All right. In an earlier lesson, we did a thermodynamic analysis of equilibrium involving a pure substance. And so in this lesson, we're going to look at mixtures, equilibrium involving mixtures. And we're going to start off with a discussion of partial molar quantities. Since, if you remember, chemical potential is what we use to analyze equilibrium. And chemical potential, we define that to be the partial derivative of G with respect to the number of moles at constant temperature and pressure. Okay, so we say that chemical potential is this type of derivative is called a partial molar quantity. So the chemical potential is partial derivative of G with respect to the number of moles at constant temperature and pressure. So let's try to get a better understanding of partial molar quantities in general first. Okay. So any extensive property X of a mixture can be written as a function of temperature, pressure, and number of moles of each of the components of your mixture. Okay. So we can write dx then to be partial of x with respect to temperature at constant pressure and number of moles dt plus another partial derivative dp plus another partial derivative times dn1 plus another partial derivative times dn2 and so on. So what partial derivatives go here? This would be partial derivative of x with respect to p holding temperature and number of moles constant. Okay, this thing right here would be partial derivative of x with respect to number of moles of component 1 holding temperature, pressure, and the other number of moles. Okay, so we're just going to call this n others constant. And this thing right here would be partial derivative of x with respect to n2 moles of component 2 at constant temperature, pressure, number of moles of other components. Okay, and then you have additional terms there depending on how many components you have. All right, now, as I said, the partial derivative with respect to moles at constant temperature and pressure is called a partial molar quantity. It's a molar quantity if you're dealing with a pure substance, but when you're dealing with mixture, it's called a partial molar quantity. So partial molar x of component 1 would be partial derivative of x with respect to moles of component 1 holding temperature and pressure constant and holding the number of moles of other components constant as well. Okay, so we use a bar above the symbol for the property, for the quantity to indicate partial molar quantity. So chemical potential can also be written as G bar. Okay, so what this means then is this expression for dx. Okay, we can rewrite that as constant temperature and pressure. This term will just drop out. dt is going to be 0 and dp is going to be 0. So dx at constant temperature and pressure is just going to be x1 dn1 plus x2 dn2, okay, plus x3 dn3 and so on. Okay, notice that this one is x1, partial derivative with respect to n1, and this thing right here is x2 bar, that's partial derivative of x with respect to n2. Okay, now you can also show that x, okay, would just be equal to n1 x1 bar plus n2 x2 bar plus and so on and so forth. We'll illustrate that using something more something that we can easily visualize, something we're very familiar with, and that's volume. Okay, that's what we're going to do now. So let's look at an example here. Partial molar volume of component 1 is V1 bar, partial molar volume of component 2 is V2 bar. And we said earlier that at constant temperature pressure, dV at constant temperature pressure is V1 bar dN1 plus V2 bar dN2. Okay? So let's show that, in fact, from this, we can also show that V is just equal to N1 V1 bar plus N2 V2 bar. Okay, so let's imagine a mixture, okay, of, oops, hold up. Okay, so let's imagine a mixture, okay, and that has N1 moles of component 1 and 2 moles of component 2. And let's imagine that we're going to increase the total number of moles by dN, okay, infinitesimal amount dN, without changing the composition. Okay, in other words, there's going to be a proportional increase in the moles of component 1 and 2 according to their mole fractions. So the mole fractions will remain the same. So dN1, okay, remember, mole fraction of component 1 is just moles of 1 over total moles, right? So if I change so I can write N1 equals mole fraction of 1 times N. So I can say dN1 is just mole fraction of 1 times dN. Okay? So here, dN1 is mole fraction of 1 times dN. So dN2 would be mole fraction of 2 times dN. All right. So given that, okay, you can say then that dV right here is V1 bar. Instead of writing dN1, I'm going to write x1 times dN. Note I'm factoring out dN here. Plus, this is V2 bar right here. And dN2 is just x2 times dN. Alright? So, I'm just rewriting this equation up here in terms of mole fractions and dN. Now, V1 bar x1 plus V2 bar x2, okay? Since we're fixing the composition of our mixture, the mole fractions are fixed, and we don't expect V1 bar and V2 bar to change because those are intensive properties. So this expression right here will just be a constant. So it's constant times dN. Okay. So partial molar quantities are intensive properties. If you're not changing the composition of your mixture, the relative composition of your mixture, okay, those will not change. So it's constant times dN. So if we integrate both sides of our equation here, integral of dV and integral of constant dN, okay, then you get V would just be equal to constant times N. Okay, integral of dN is N plus an integration constant. Okay. Now, if N is 0, if you don't have any moles, then your volume is 0. So if you plug in 0 here, then your volume is 0. So that integration constant is just going to be 0. Okay, so we can say that V is just whatever that constant is times 10. And that constant we showed earlier was V1 bar x1 plus V2 bar x2. So here we've just shown that volume is equal to V1 bar x1 plus V2 bar x2 times N. Okay? But x1 times N is just N1, and x2 times N is just N2. So we have shown that our volume is in fact equal to N1 V1 bar plus N2 V2 bar. Okay? So that's what we have shown here. We've shown that our volume, okay, not only is dV equal to V1 bar dN1 plus V2 bar dN2, but we've also shown that V is equal to V1 bar N1 plus V2 bar N2. Now you can define the molar volume, V sub m, or you can write that as V bar as V divided by N. So you can see that that's just going to be, what would that be? Okay. If you divide both sides of this by N, okay, then that's just V1 bar X1 plus V2 bar X2. Okay? So that's your molar volume. Alright, so let's check if we understood the concept. Let's say you have a 50% mass, 50% mixture, 50% by mass mixture of ethanol and water. And that mixture happens to have a density of 0.914 grams per mil. If the partial molar volume of water is 17.4 mils per mole, what's the partial molar volume of ethanol? What's the equation we need to use here? We say that V equals N1 V1 bar plus N2 V2 bar. Okay. Do we know our volume? We know our density. So, and then we're just given the percentage of the water and ethanol by mass. So let's just assume we have 100 grams. Okay. Since partial molar volumes are intensive properties, they don't depend on the actual amount. It only depends on the composition and the concentrations of your components. So let's say you have 100 grams. So that means you have 50 grams of water and you have 50 grams of ethanol. Okay? So what would be the volume of our mixture? Okay. Remember, density is mass over volume. So volume would just be mass over density. Okay. So our volume is 100 grams divided by 0.914 grams per mil. Grams cancel out. Let's see what that is. 100 divided by 0.914. That gives you 109.4. Okay. 3 sig figs. We'll treat 100 as exact. Okay, so 9 here is your last sig fig. So that's your volume in milliliters. Okay, so we know our volume. Okay, what else is given in this problem? You're given the partial molar volume of water. Let's call component 1 our water. So this is 17.4. So we're going to say water is component number 1, ethanol is component number 2. So we know the partial molar volume of component 1. We know moles of component 1 because we're assuming 50 grams. Okay, so divide that by 18.016 grams per mole. And we know the moles of component 2 because we also have 50 grams of ethanol. So I divide that by the molar mass of ethanol, which is, what's ethanol? Let's see, molar mass, 2H5OH, okay, 46.07 grams per mole. 46. Boy, let's have an extra sig fig there. Just 46.068. Okay. 46 point. So you divide that by 46.068 grams per mole. So we have all the information we need. We just need to solve for V2 bar. Okay. So let's do that. Let me do that quickly on MathCAD for you. Let's see. So we have your given V water is 17.4 milliliters per mole. Okay, and our volume was 100 over 0.914 grams per mil. So 100 grams. So our volume is many milliliters, 109.4. Okay, number of moles in water is 50 grams divided by 18.016 grams per mole. So in moles of water is 2.775 moles ethanol equals 50 grams divided by 46.068 grams per mole. So moles ethanol equals that 1.085. And what was our equation? Volume equals N water times partial molar volume of water plus N ethanol plus partial molar volume of ethanol. Okay, so I want to solve for partial molar volume of ethanol. So I go symbolic, variable, solve, and that's the expression. Okay, so partial molar volume of ethanol equals that. Oops, I didn't get it right. Okay, I forgot to multiply this by moles of ethanol. Okay, so solve for volume of ethanol, partial molar volume of ethanol, and that's the expression. Of course, you should be able to do this manually. Equals that. So, okay, V and water. Okay, doesn't like something. It doesn't like. V water is mils per mole. Volume ethanol. What doesn't it like? I've got N water, V water, and ethanol. Oops, okay, I have made a mistake here. This is just be, okay, moles water, partial molar volume of water, plus moles ethanol, partial molar volume of ethanol, okay? Something wrong with my formula. So if I solve for partial molar volume of ethanol, variable, solve, okay, that's better. Copy and paste that here. So partial molar volume of ethanol equals this many mils per mole. 56.3 milliliters per mole. That's how you solve for it. Okay? So going back, let's move on. So how do we determine partial molar volumes in the first place? In the earlier problem, you're given one of the partial molar volumes, but how do you determine the first partial molar volume to begin with? Well, typically what you do in the lab is you prepare a series of solutions of known molalities. Okay, so that's why partial molar volume is also known as partial molar volume. Okay, so at constant temperature and pressure, you measure the density of these solutions. Okay, and then what you do is you calculate the volume of each of these solutions that is going to contain 100 grams of solvent. We can treat, for example, water as our solvent. So what would be the volume based on the density? Okay, the volume would be what? If your dent is going to be the mass, right, of your solution divided by the density of the solution. Okay, so that's grams divided by grams per ml. What gives you mils? What's the mass of our solution? It's going to be 1,000 grams of solvent plus how much solute do we have? N2 is the moles of solute times the molar mass of your solute, which is M2. Okay, so for example, if you have ethanol, you might say you have 0.1 mole of ethanol times 46 grams per mole. That would give you grams of ethanol. Okay, so 2 here, we're using the label 2 for solute divided by the density. So you can calculate that from your experimental data. Okay? But the number of moles of solute is just the molality. Why? Because you have 1,000 grams of solvent. Okay? So you can also say that the volume of your solution is just going to be equal to 1,000 grams of solvent plus the molality times M2. So let's just take out the units here. Let's use numerical values divided by the density in grams per ml. Okay? So if you have N molality times 1 kilogram for unit consistency, that's just number of moles. So that's just just use the numerical value there. Okay? Now, so how do you get partial molar volume then of component 2? Then you can just say partial molar volume of component 2, okay, would just be, by the way, what you would do, all right, is you would plot the volume versus number of moles of component 2 or versus molality, okay? So versus N2 or molality. So you might have data that looks like this, right? Let's say you have data that looks like that. And so what you do is you take the derivative, so you plot, you express V as a function of molality, okay? And, or V as a function of N2 actually, which is the same as molality. And you take the derivative of that with respect to N2, so the slope of the tangent line, so dV dN2 will just be your partial molar volume of component 2. All right, so once you know the partial molar volume of component 2, okay, that's dV dN2, which is just dV dM, then you can solve for partial molar volume of component 1 for any given mixture. Whatever the V is for that mixture, you subtract V2N2 over N1. Where does that come from? Remember you said V is N1 V1 bar plus N2 V2 bar. Note that I'm not putting bars on here anymore. There should be bars there. And so I can say V1 is equal to V minus N2 V2 bar over N1. Okay, so that's how you'll do it. Let's look at an example. This is illustration 5.1 in Atkins. Let's say you have a mixture of water and ethanol, okay, and molality, M here is the molality of ethanol, so moles of ethanol per kilogram of water. In this particular situation, the volume is found to depend on the molality. So the volume that contains 1,000 grams of water depends on the number of moles of ethanol added, and the number of moles of ethanol added is just numerically equal to whatever the molality is, right? So suppose it's given by this equation. You have experimental data of volume versus molality. You're able to fit that to a cubic equation, A plus BM plus CM squared plus DM cubed. That should be easy to do in the lab, right? And where A values of A, B, C, and D are given here. 100,002.93, 54.6664 for B, negative 0.36394 for C, and 0.02825 for D. So let's determine formula for the molar volume of ethanol and water for a range of solutions going from pure water to a 10 molar solution of ethanol. Okay, so let's do that on MathCAD. Let me create a new document. All right. So what did we say we have here? Our volume is a function of molality. So we say volume of M is a function of molality is A plus B times M plus C times M squared plus D times M cubed. Okay, MathCAD is complaining it doesn't know what A, B, C, and D are, so let's type the value for A. A is 1002.93, and B is 54.6664. Okay, and C is negative 0.36394, and D is 0.028256. 0.028256. Okay, let me just make sure I have that right. Okay, A is 1002.93, B is 54.6664, C is negative 0.36394, and D is 0.028256. All right, I got that. All right, so we can say then the partial molar volume of ethanol, which is component number 2, okay, is just equal to the derivative of V with respect to M, which in this case is just going to be B, plus 2 times C times M, plus 3 times D times M squared. Okay? So that's the partial molar volume. So let's plot that from molality equals 0 to 10. So 0, first molality. Our next data point will, let's just say, take it at 0.1 molality and up to 10 moles of ethanol added to our 1,000 grams of water. Insert a graph. Let's plot V2 of M versus M, and that's our partial molar volume. Okay, so whatever, if just plug in the molality you want, you now have the partial molar volume of ethanol. Okay, how do I get the partial molar volume of water? V.1 of M, which is V equal to V of M minus, what was our equation? Okay, P equals, it's going to be equal to N1 V1 bar plus N2 V2 bar. Okay, but our N2 is molality. What is our N1? Our N1 is 1,000 grams divided by 18.016 moles. Right? So that's our N1. And so we can solve for our V1 bar is just equal to V minus N2 V2 bar divided by N1. Okay, so that's our formula. Write that formula down. So that's going to be V minus N2, which is molality, times V2 of M, space bar divided by, oops, divided by N1, and N1 here is 1,000 grams divided by 18.016 grams per mole. And I'm just leaving out the units. So that's your molar volume of water, partial molar volume of water. So if you were to do that plot, insert graph, XY plot, I'm going to plot V dot 1 of M versus M, and that's what I get. Okay? One thing you'll notice here is as your partial molar Gibbs and partial molar volume of your ethanol is dropping, you'll notice your partial molar volume of water is rising. Okay? And then down here, when your partial molar volume of your ethanol is going up, okay, you'll notice your partial molar volume of water is going down. That illustrates what's known as the Gibbs Duhem equation, which is a very important equation for us. All right, so let's continue. Let's talk about the Gibbs Duhem equation now. All right, so we said that the volume of, we're going to illustrate that using the Gibbs Duhem equation, using volume. We said volume is equal to partial molar volume of component. If you have a two-component mixture, so it's going to be partial molar volume of component 1 times the moles of 1 times partial molar volume of component 2 times moles of 2. All right, so now let's imagine you have a mixture, okay, of 1 and 2. And we're going to change the composition of our mixture. We're going to change what could cause a change in total volume. Well, we'll be changing the number of moles. All right, so we're going to make the generic assumption, look at the generic case where the mole fractions don't remain constant. Okay, so V1 and V2, the partial molar volumes, could be changing because you're changing the mole fractions of your components. So in general, then, you say that the change in the volume at constant temperature and pressure, that's dV, is equal to V1 dN1 plus N1 dV1. So derivative of product, right? The first times the derivative of the second plus the second times the derivative of the first. You do the same thing with differentials. And then V2 bar times differential of N2 plus N2 times differential of V2. So that would be the expression for dV, total change in volume. But we've already established earlier that the V1 bar dN1 plus V2 bar dN2, this expression right here, is equal to dV. So that means this term right here plus this term right here must be equal to 0. So we say N1 dV1 bar plus N2 dV2 bar must be equal to 0. This is called the Gibbs Duhem equation. Basically what it's telling you is that in this two-component system, V1 bar and V2 bar are not actually independent of each other. Okay? As we've seen earlier, okay, in the math document, see that as V2 bar decreases, V1 bar actually increases, and as V2 bar increases, V1 bar actually decreases. Okay, so we can rewrite this equation in a slightly different form. We can say that N1 is mole fraction of 1 times total moles, and N2 is mole fraction of 2 times total moles. Okay, so we can rewrite it that way. So you can also say that, and you can factor out the N, right? And then since the whole thing is equal to 0, N will just cancel out. So you can just say that x1 dv1 bar plus x2 dv2 bar must be equal to 0. Or you can rewrite this to say dv1 bar equals negative x2 over x1 dv2 bar. Okay? Or you can say dv1 bar over over dv2 bar is negative x2 over x1. You can see it's a negative number. Okay, so as you're monitoring the change in partial molar volumes, as one goes up, the other one goes down. So if your dv1 bar increases, your v1 bar increases, that would be positive. Then your v2 bar would have to decrease, so dv2 bar would have to be negative, and vice versa. Okay, so you can write your Gibbs Duhem equation this way using mole fractions. Okay. Right. Or you can rewrite it in this form. Or since the ratio of mole fractions, since x2 over x1 is the same thing as n2 over n total, and x1 is for x2 over n1 over n total. So mole fraction of 2 is moles 2 over moles total. Mole fraction of 1 is moles 1 over moles total. And cancels out. You can also say it's equal to negative n1 over n2 over n1 dv2. Okay, and basically, like I said, what this is saying is as v1 increases, okay, partial molar volume of component 1 increases, partial molar volume of component 2 decreases. And I've been a little sloppy here. These should all have bars on them. Okay, v1 and v2. So what this is saying, like I said, in general, you can say if you have an n component system, only n minus 1 of those partial molar quantities are independent. Now, looking ahead, we're going to use this to relate chemical potentials, okay? The chemical potential of a solute to a solvent, because sometimes changes in the chemical potential of a solute are not easily monitored, but you can it's not easily determined, so you can express it in terms of the changes in the chemical potential of the solvent. All right. So let's go back to that problem we had earlier. Remember, we figured out the partial molar volume of ethanol in water if we knew how the volume of a solution containing 1,000 grams of water depends on the molality of ethanol. All right. Let's see if we can determine using the Gibbs Duhem equation. So this would be an alternative way of determining the partial molar volume of component 1. Remember, we said V2 here is just dV dm, right? And we solve for V1. Based on that. Let's use the Gibbs Duhem equation this time to solve for V1. Okay? Now, if you recall, your Gibbs Duhem equation says dV1 equals negative integral of n2 over n1 dV2. Right? Now, so if I were to integrate both sides, it should be integral of dV1. Okay? So if I were to integrate both sides, okay, from let's say molality 0 to whatever the molality is. So from pure 1, remember 1 is water, right? 1 is water. To whatever the mixture is. So from pure water to a mixture. What would that be? Integral of dV1 would be V1 bar, and I forgot the bar there. So that's V1 minus V1 pure. I'm going to use a star because the integral of dV1 must be V1 bar minus V1 bar pure equals negative integral of n2 is molality, right, over n1. n1 is constant here, which is 1,000 grams. I'm just going to keep that at n1. n1 is 1,000 over molar mass of water, 18.016 grams per mole, right? M over n1. And then instead of writing instead of writing dV2, okay, I'm going to change my integration variable. I'm going to say dv2 dm. Okay, notice that this would cancel this one out, right? But I'm going to write it this way because I know what v2 bar is as a function of m, right? So I'm going to do that. So from pure, and the reason for that is it makes it easier to set my integration limits. So from pure water, molality is 0, up to whatever the molality is of the mixture. So we can therefore calculate V1 bar is V1 star minus integral of m over n1 partial molar volume of component 2 with respect to molality from molality equals 0 to whatever molality you're interested in. Since molality is just a dummy variable, we can put an m prime there if you want. Okay? So that's how you can calculate the molality. I mean the partial molar volume of component 1 from the partial molar volume of component 2 using the Gibbs Duhem equation. So let's do that with MathCAD. Let's verify that we get the same answer. Okay. Alright. So I'm going to define a different Gibbs Duhem equation here. A different expression for V1M. Okay. So I'm going to V1 using the Gibbs Duhem equation. So V1GD, I'm going to call that of M equals, okay, that is V1, okay, partial molar is molar volume of water if it's pure, so that's when the molality is 0. So that's V1 at 0, right? Minus integral, my toolbar, oh, my toolbar's over here, okay, minus the integral from molality 0 to molality m of molality over N1, which is 1,000 grams over 18.016 grams per mole, okay, times the derivative of V with respect to M, okay, derivative of V2 with respect to M. So this is going to be dm, and this is going to be 1. The derivative of V2 with respect to M would be 1. It's going to be dV2 dm is going to be equal to 2c plus 6dm. Okay? So 2c plus 6dm. So scroll down here, you say 2 times c plus 6 times d times m. There. Alright, so let's compare that. Let's plot that now. Okay, so V1 of m versus m looks like that, and let's compare V1 using the Gibbs Duhem method, m versus m, and you get the same result. Okay? So it just overlays. So let me just do this. There. Okay. And if you compare that with the direct calculation, you get the same thing. In fact, if you were to calculate, let me see. I'm just going to offset the other one with just a little. What are these numbers, by the way? Let's see. Okay, I'm just going to offset the other curve by maybe point 2, so you can see that they're in fact the same. Okay, so I'm just going to say v dot 1 of m plus 0.2 there. So you can see they are the same. If I took out that point 2, they're just right on top of each other. So that's how you use the Gibbs Duhem equation. If you know how one partial molar quantity changes, you can figure out how the other partial molar quantity changes. All right. Another way you can determine partial molar volumes is using what's known as the method of intercepts. And what you do here in the lab is you prepare a series of solutions that have a known moles of components 1 and 2. Okay, so if that's the case, then you say the volume is just V1 bar times N1, which is X1 times N, okay, plus V2 bar times N2, which is just X2 times N, okay, and where N is just the total number of moles, N1 plus N2. Now you plot the molar volume. Molar volume is V divided by N. So V divided by N give you, this is going to be equal to V1 bar X1 plus V2 bar X2. Okay. So you plot that versus mole fraction of X1. And you should be able to show that the derivative of the molar volume with respect to mole fraction of 1 is just V1 bar minus V2 bar. Okay, how do you do that? Well, let's see. If you take dVm, so again you do the first times the differential of the second, so V1 dx1 plus the second times the differential of the first, so plus x1 dv1, okay, and again you need bars there for the v1, plus the first times the differential of the second, so that's v2 bar dx2, plus the second times the differential of the first, x2 dv2 bar, okay. Now, if we use the Gibbs Duhem equation, what do we know from the Gibbs Duhem equation? From the Gibbs Duhem equation, we know that V1 bar dx1 plus V2 bar dx2, okay. Sorry. If we know from the Gibbs Duhem equation, you know that x1 dv1 bar plus x2 dv2 bar should add up to 0. So these two will cancel each other out, right? So v1 bar dx1 plus v2 bar dx2 will just be your dv. Okay, so once you have that, this expression simplifies to this. But we know that if the mole fraction of one increases, the mole fraction of the other one decreases. In fact, okay, mole fractions add up to 1, so dx1 plus dx2 must be equal to 0. So if dx1, if your mole fraction went up by 0.1, mole fraction of the other component will go down by 0.1. So dx1 is equal to dx2. That means you can write dx2 is just equal to negative dx1. So that means, let me rewrite that down here. Here you have our dv, this one, rewrite that one, equals v1 bar dx1 plus v2 bar dx2. Let's rewrite that. That's going to be v1 bar dx1 plus v2 bar negative dx1. So you can see that that's v1 bar minus v2 bar dx1. So that means that dvm dx1 is just v1 bar minus v2. So that's the difference in the partial molar volumes is just the slope of the tangent line to your plot of v sub m versus x1. Okay, so if I were to plot molar volume versus mole fraction of component 1, okay, the range of values for mole fraction is 0 to 1, right? So if I have data that looks like this, let's just say, let's just say I have data that looks like this. Okay. Then at this particular for this particular mixture right here, okay, the slope of the tangent line is going to be equal to, the tangent line is V1 bar minus V2 bar. Okay, and we can actually show that this thing right here is in fact equal to V1 bar. Okay, now this one right here is V1 bar pure. Okay, this thing right here is V1 bar for this mixture that we have over here. And we can also show that this thing over here, this y-intercept, is equal to V2 bar. Why? What's the slope there? V1 bar minus V2 bar over 1 minus 0, right? Delta x is 1 minus 0. That's just equal to your slope, dVm dx1. Okay, so that's the slope of the tangent line to that graph of molar volume versus x1. So that gives you the difference. So we've shown that. Okay, so what's the equation of the tangent line? The equation of the tangent line is this. The molar volume according to the tangent line would be equal to x1 times the slope plus the y-intercept. You can show that that y-intercept is equal to V2 bar. Okay, as I've shown, as I illustrated down here, that intercept is V2 bar. Okay, how do you show that? Well, in your tangent line, this is y equals okay, this is y equals mx plus b, right? So that b is the y-intercept. Okay, and so we can show that that is equal to V2 bar. How are we going to do that? Well, let's go back to our equation. V equals, V sub m is x1 V1 bar plus x2 V2 bar. We know that, right? So we can rewrite this as x1 V1 bar plus 1 minus x1. Remember, x1 and x2 add up to 1. So x2, instead of writing x2, I can write 1 minus x1 times V2 bar. So I can rewrite this. I can say that that's going to be x1 times V1 bar plus V2 bar minus x1 V2 bar. Okay. So we can say then that I can combine these two. I could say V1 bar minus, so this 2 right here, V1 bar minus V2 bar times x1 plus V2 bar. So that's your molar volume right there. Okay, so this is generally true. Now you might be tempted to think that this is y versus x and that's your slope and y-intercept. That's not, and you can say that could have been an easy proof that that's a derivative. No, that won't work because we know that as your mole fraction is changing, V1 bar and V2 bar will be changing as well. Okay, so these won't be constants as your mole fraction is changing. Okay, so that would be a faulty derivation. But it just turns out that this is your slope. Okay, this is the slope of your tangent line at x1. So if you plug in Vm at x1 and the slope of the tangent line at x1, then you should be able to show that the y-intercept of that tangent line is equal to V2 bar. Okay, so similarly, you can show that the intercept at when mole fraction of 1 is 1, then the intercept of the tangent line is V1 bar. Okay, so bottom line here is if you were to plot molar volume versus mole fraction of component 1, okay, at x1 equals 0, your tangent line will cross your VM axis at V2 bar, and at x1 equals 1, okay, the equation, your tangent line, the value of your tangent line would be equal to V1 bar. So that's why it's called the method of intercepts. Okay, so let's use the method of intercepts now for the same problem we talked about earlier. Okay, so same problem. So dVm dx1, remember we said let's show that that is in fact equal to V1 minus V2, V1 bar minus V2 bar. So how are we going to do that? We already have the expression for Vm, right? And so we just have to know how to express molality instead in terms of mole fraction. So what's mole fraction of component 1 in terms of molality? Okay, so mole fraction of component 1, so you have 1,000 grams over 18.016, that's moles of water, right? So moles of 1 divided by the total moles would be whatever the molality is plus moles of water, which would be 1,000 over 18.016. Okay? So that's our x1. Okay, hold on. Okay, let's continue. So this, let me just rewrite this as N1, moles of component 1 to make things easier to read. So this is going to be equal to N1 over M plus N1. Okay, so what do I need to do? I need to take the derivative of M with respect to x1, the derivative of V sub M. So d of V sub M with respect to x1. I can use the chain rule for that. I can say that's the derivative of Vm with respect to M, because I know how V sub M depends on M, okay, on the molality. And then I'll take the derivative of M with respect to x1. Alright, since I already have my x1 expressed in terms of M, it might be better for me to flip it. So I'm going to say this is derivative of V sub M with respect to M times 1 over partial of derivative of x1 with respect to M. Okay? Now, so it's going to be dV sub M with respect to M divided by, and this thing right here, okay, let's take the derivative of that. Let's see, x1 equals n1 over m plus n1, so should be able to show that dx1 dm is equal to negative n1 over m plus n1 squared. Okay, let's see. Let u equals m plus n1. Okay, then so we say du is equal to, and then you can say dx1 dm, okay, is equal to dx1 du times du dm. That makes it easier. So if you write this as n over u, that's going to be minus n over u squared, and du dm is just equal to 1. So n over u, and u squared, and u is just m plus n1. So this thing right here is going to be negative n1 over m plus n1 squared. Okay? So let's do that in MathCAD. So here I've done it for you already. So here we define n1 is 1,000 over 18.016. V as a function of molality, the molar volume, is the volume right here, A plus BM plus CM squared plus DM cubed, okay, divided by the total moles, which should be moles of component 1, moles of water, plus the molality. So the molality would be the number of moles of component 2, since we have 1,000 grams of component 1. All right? So that's the molar volume as a function of molality. The mole fraction as a function of molality, as we said earlier, is moles of component 1, which is constant, 1,000, divided by the total number of moles, which is moles of component 1 plus the molality. So that's mole fraction. So the derivative of V sub m with respect to m, take the derivative of this expression with respect to m, and you get this one right here. Okay, let's see how that's done. All you have to do is, after you've entered that expression on MathCAD, you'd say, okay, let me just copy that expression. Copy. I'll paste that over here. Okay, all you have to do is click on the variable you want to differentiate with respect to. And so go to symbolics, variable, differentiate. And this expression right here, that's the one we have. This expression right here, this is the one we have down here. Okay? Let me get rid of that. So what we have here is the derivative of the molar volume with respect to molality. Okay, so that's the expression. And then what you do is take the derivative of mole fraction with respect to molality. We did that earlier. We did that manually. It's just negative n1 over m plus n1 squared. So that's what we have here. Negative n1 over n1 plus m squared. That's the derivative. So this is d of x1 dm, and this is d of vm with respect to m. It's a function of molality. Okay? So once you've done that, you just take the ratio. So this is the derivative of molar volume with respect to mole fraction 1, this one right here, is equal to the derivative of the molar volume with respect to molality divided by the derivative of mole fraction 1 with respect to molality, this one down here. Okay, so we have an expression, it's a function of m, molality. And so we said that this thing should be equal to V2 bar minus V1 bar. Okay, so let's plot that. Here's the plot. That's what it looks like. Okay, so versus molality. This is dVm dx1. Okay, so what we're plotting here is derivative of molar volume with respect to x1 versus molality. And that, we said, should be equal to V2 bar minus V1 bar. So let me go ahead and put V2 bar minus V1 bar in there. Add it to that graph. So V2 bar, so V2 as a function of molality minus V1 as a function of molality. Oops, sorry, it should be V1 minus V2. Sorry, V1 minus V2 bar. V1 bar minus V2 bar. Okay, so this is V1 M minus V2. And you can see both curves are identical. Okay, so if you want to, let me put an offset there so you can see them better. I'll just offset this by 0.01 by 0.1, so you can see those two curves slightly off from each other. Okay, So they are identical. In fact, if you want to plot, oops, another way you could plot this, insert graph. Let's see. Is to put something like this. So plot versus molality. You have dVm dx1 of m minus the quantity v dot 1 m minus v 2 m. And you can see there's some, it's essentially zero. See, this goes from 2 times 10 to the negative 14 to 2 times 10 to the negative plus or minus negative 2 times 10 to the negative 14. So that's just round off errors right there. So that's essentially zero. Those two are essentially the same thing. Okay? Now it's 2 times 10 to the negative 14 difference compared to the actual values, which are 36, 34, 30, negative 34 to negative 38. So this 2 times 10 to the negative 14 is a very small number. So that's essentially zero difference between the two groups. Okay. So let's pause here for now, and we'll continue this in another video. All right?